Good evening all. Today we are going to discuss about transient response of series RLC circuit with DC excitation. Series RLC circuit will be a second order circuit. Second order circuit in the sense the differential equation obtained by applying the KVL will look like d square y by dx square plus dy by dx plus y is equal to 0 like this. The order 2 tells it is a second order differential equation. So this order of the differential equation is decided by the number of energy storing elements in the circuit. That means if energy storing elements are inductor and capacitor, if the both are there in that circuit, then the order of the differential will be second order. Now let's derive the equation for current equation I of t for series RLC circuit. Let's draw the series RLC circuit. At t equal to 0, the switch closes. Before that, all initial conditions are 0. That means IL inductor initial current will be 0. Capacitor initial current will be 0 volts. So now applying the KVL across this circuit. Beginning from here, minus V plus current direction is this one, so positive negative, R into I of t plus L into di of t by dt plus current we know capacitor current we know that IC is equal to C dVc by dt. Here we need the voltage across the capacitor, so we will be writing this in terms of current. 1 by C integration I of t dt. As capacitor current and inductor current are same, so we can take IC as I of t. Now we will be writing this time domain into frequency, and we will derive the current equation. We Laplace transform on both sides. I assume you will be knowing that Laplace transform basics. So by assuming that, I will be just writing the Laplace transform for each. Laplace transform of V is minus 1 by S plus R into I of S plus here V of S plus L into 1 derivation. Laplace of derivation will be S is multiplied, so I of S plus 1 by C integration will become 1 by S. I of S is equal to 0. Therefore I of term will be taken at one side, that will be R plus SL plus 1 by SC is equal to this voltage will be taken that side, V of S by S. Sorry, here V is a step response, that means DC voltage, so it is not a time variant, so it is a constant, so V, not S. So I of S will be V by S into 1 by R plus SL plus 1 by SC. For this 1 by V by S, we can take SC as LCM. So now R into SC plus S square LC plus 1. Divided by 1, it is a reciprocal, so V by S into SC by, if you take LC as a common, here LC as a common from this, so S square will be written first, and LC we can write this as C is an C is also a term, so this is taken common. R is not here, so R by L into S plus LC is taken common, so 1 by LC. Here S and S will be cancelled out, C and C will be cancelled out, so V by L into 1 by S square plus R by L S plus 1 by LC. This is the expression for current in frequency domain. For this, if you do the partial fractions, and we will reconvert into time domain. That means we can write this as, we can assume this roots as V by L 1 by SSR plus RLS plus 1 by LC can be written as 1 by S minus S1 plus B by S minus S2. Yes, this now if we apply the partial, this is by partial fractions. If you do Laplace transform, it will be it is a common to find the partial fractions for any equation. For this, to find A, then that will be 1 by here this is written as A by S minus S1 plus B by S minus S2, so V by L is as it is, so 1 by S minus S2 at S is equal to S1. Now at S, put S is equal to S1, so V by L 1 by S1 minus S2. There is no confuse. Here we will be comparing these two equations and we will be finding this A. When we comparing this, we will put S is equal to S1 in this equation. This is splitted into S minus S1 into S minus S2. So this we can write directly like this. B also we can write V by L 1 by, we need not to write this root, we will be writing this root minus S1, in place of S we will putting this root, as it is an computative. So if you do the partial fractions in this way, then it will be easy. Or else if you do LCM, compare this equation, and if you find this, it will be the same value, V by L by 1 by if you put in place of S2, and if you take minus out, then it will be S1 minus S2. Then if you rewrite the equation, V by L, A is 1 by S1 minus S2 into 1 by S minus S1. This is first expression, plus B. Here we write it as minus, so we will take minus V by L S1 minus S2 into 1 by S minus S2. In this we will take V by L into 1 by S1 minus S2. It is as it is a roots, it is a constant value, so remaining terms we will write here 1 by S minus S1 minus 1 by S minus S2. So by applying inverse Laplace transform, then it is I of S. I of S will be I of t is equal to as it is a constant, we will represent this as k1, and 1 by S minus S1, for this we can write as e power S1 of t minus k2 e power S2 of t. As we can take this minus will be included in this constant, we can take it as plus. This will be the current equation. Based on the roots, the response will be, the current response will be changing. In the time domain, we obtained k1 e power s1t plus k2 e power s2t. This s1, s2 are obtained by this roots. If you obtain these roots, if you place the roots here, then the response of this current transient response will be derived. So for this roots, we will be obtaining these roots. As it is a second order, the formula for this is minus b. B is r by L. Minus b plus or minus under root of b square minus 4 times of a into c. A is the s square coefficient, c is the 1 by LC, by 2 times of a. A is 1, so 2. Now we can simply write as r by 2l plus or minus under root of r by 2l whole square minus, if you multiply 2 inside, then 4, it will become 4 cancelled out, 1 by LC. We can write as root and square. We can do like that. Now we can write alpha. We can take as a constant alpha. R is equal to alpha is equal to r by 2l, and omega n. Another term is this one. We can write it as 1 by root LC. And we can also take damping ratio. Zeta. This zeta value is if you increase this zeta value, the oscillations will be reduced. Oscillations can be reduced. Zeta value will opposes the oscillations. Oscillations in the response. Zeta value is alpha by omega n. Alpha value is r by 2l by under root of LC. Therefore 1 by root LC. 1 by root LC. You can write here r by 2l into 1 by root LC. That means r by 2l into root LC. Therefore we can write r by 2 root c by l. Zeta is equal to, we can write like this. We can write now alpha is equal to zeta omega n. We can write in this fashion also by considering zeta is equal to r by 2 root l by c. So by varying alpha, zeta value, by varying zeta value, alpha will be varying. Case by case we will see how if alpha is varying, indirectly zeta is varying. So case by case we will be seeing. Case 1, our roots are minus r by 2l plus or minus under root of r by 2l whole square minus 1 by root LC whole square. This one we can write as minus alpha plus or minus under root of alpha square minus omega n square. This one roots for S1, S2, first root and second root. If alpha is greater than omega n, this is the first condition. If alpha is greater than, then if alpha is greater than, then it will all be a real value. So overall the S1 root will be minus alpha plus under root of alpha square minus omega n whole square. S2 root will be minus alpha minus under root of alpha square minus omega n whole square. Two roots. We will put this in our current what we got in the equation. K1 e power S1t plus K2 e power S2t. By placing this S1 S2, K1 e power minus alpha plus under root of simply we can write beta is equal to under root of alpha square minus omega n square. For simplification we will write it as beta into t plus K2 e power minus alpha minus beta into t. If we further simplify, it will look like e power minus alpha K1 e power beta t plus K2 e power minus beta t. So for this is the response of if alpha is greater than omega. The response will be looking like based on the alpha, that is zeta value. If the zeta value is 2, this is the response. If the zeta value is more, 4, and zeta value is 2. Based on the zeta value, the response will be looking like this. For second case, case 2, if alpha is equal to omega n, in this case S1 will be alpha is equal to minus alpha plus here under root of alpha square minus omega n square. In this, alpha is equal to omega n. If you put this value will become 0. Therefore S1 is equal to S2 is equal to minus alpha. Both roots are same. For this we will keep this S1 in the our equation, k1 e power minus alpha t plus k2 e power. As the roots are same, t should be added in the as it is a linearly dependent, t will be added to it. We will be discussing this in next topic, in maths topic, why it is t is added. Based on that we added here. So for this the response will be, this response is critically damped. Previous response is over damped. For case 3, we will consider alpha is less than omega n. That means first root will be minus alpha, let assume plus or minus under root of alpha square minus omega n square. If alpha is less, then the overall expression will be in the negative. So if you take negative outside, under root of, then it will look like minus alpha plus or minus under root of minus 1. If you take common, omega n minus alpha square. This minus 1 is the j value is under root of minus 1. Then minus alpha plus or minus j under root of omega n minus alpha square. This is the first root and second root. First root will be minus alpha plus j under root of omega n square minus alpha square. Second root will be minus alpha minus j under root omega n square minus alpha square. For this we will keep in our current what we got the equation, k1 e power minus alpha plus j under root of omega n square minus alpha square into t plus k2 e power minus alpha minus j under root of omega n square minus alpha square into t. If we expand it, then e power alpha t is common in all, that is e power minus alpha t will be outside. Then e power, we know e power j theta is the cos theta of we can take j theta means cos theta plus j sin theta. Based on this, in that place of theta there is an expression of omega n square into t, that we will replace. Then this constants, if we write this one here, 1 k1 k2 also for this one. So overall will be k1 plus k2 for cos terms. We will let omega d is under root of omega n square minus alpha square. Then it is an omega d into t plus j times of k1 minus k2 sin omega d into t. Therefore, this is the current equation. For this, the response will be as these are cos and sine waves, it will be combination. Is there is e power minus alpha is multiplied, so that cos and sine waves will be in the decreasing fashion. Then this is under damped condition. One more thing, in general all other books omega d value is omega d is equal to omega n under root of zeta square minus 1. As if we are taking not in terms of zeta, we are taking directly in terms of alpha. So for omega d under root of omega n square minus alpha square, this is also correct for this derivation omega d. This is for if you split alpha is equal to zeta into omega n, then this is correct. Let alpha is equal to 0, omega n is equal to omega n. In this case, S1 will be minus alpha plus or minus under root of alpha square minus omega n square, means in this we are keeping 0 plus or minus under root of omega n square. Then S will be here minus, so plus or minus plus j omega n. S2 will be minus j omega n. Then for current I of t is equal to k1 e power j omega n t plus k2 e power minus j omega n t. Then the response will be fully oscillatory. There is no decaying factor here, so there is no reduction in the oscillations. This is called undamped condition. For the roots, that is 1 by r by 2l s r minus under root of r by 2l whole square minus 1 by root lc whole square. For these roots, we can find the critical resistance where this term will equal to this term. The resistance where this term equal to this term, this is a critical resistance. So critical resistance is this, we are considering as alpha, this is omega n. So alpha is equal to omega n condition. To obtain this condition, what is the value of R value? So that we will be R critical. So RL whole square is equal to 1 by LC. We can write R critical is equal to R critical square is equal to 2L square by LC. Therefore, R critical is equal to 2L by root LC. That can be written as 2 times of root LC. R critical is 2 times of root LC. Now we are going to discuss about parallel RLC circuit. For this I am taking current source, a switch in parallel, and a resistor and an inductor and a capacitor, all are in parallel. So at t equal to 0, the switch is opened at t equal to 0. R, L and C. This is the I of S. For this we will write applying KCL. Total current IS is equal to inductor resistance current IR, IL and IC. So IR will be as we can consider capacitor voltage as V. So this V is applied across all the branches. So we will write this as V by R plus, and we will write inductor current as 1 by L under root V of dt plus for capacitor current is C dV by dt. As this capacitor voltage is time variant, so V of t. But this I of S is a constant because we are using a constant current source. So applying Laplace transform on both sides. So constant Laplace of applying Laplace on constant, it is I of S by S. It will be 1 by R V of S plus 1 by L into S V of S plus S into C V of S. So I am writing here I of S. We can write as two S's are there, we will be confusing, so I will write I by S is equal to V of S is common 1 by R plus 1 by SL plus SC. So we need V of S to be calculated. V of S is equal to I by S into 1 by R plus 1 by SL plus SC. Therefore I by S 1 by, we will take R SL as LCM factor, remaining we will be writing here SL plus R plus here S square R and LC. Now this L, it will be going top, that is RSL by we will write RLC S square plus SL plus R. Here SS will be cancelled out, and if you take RLC common, RLC as a common, then RL on the top, S square plus, here already one L is there, so remaining terms 1 by RC is into S plus, here R is there, so 1 by LC. This RL and RL are cancelled, so I by C into 1 by S square plus 1 by RC into S plus 1 by LC. This is the V of s expression. As we know, we can write we will write this 1 by s square plus 1 by RCS plus 1 by LC is equal to a times of s minus s1 plus b times of s minus s2. In this video, previously a value will be I by c 1 by s1, as it is an this is written s1 minus s2. B will be I by c 1 by s1 minus s2, as minus is taken common. So overall, if you place here, and V of s will be I by c, V of s will be I by c. In place of this, we will write a by b in this. A we got as this thing, so we already it is having it here, and 1 by s1 minus s2 into 1 by s minus s1 plus it's a minus I by c 1 by s1 minus s2 into 1 by s minus s2. So from this, V of s will be written as I by c into we can write this term as k, as it is a constant k1. Here 1 by applying Laplace transform on both sides. If you apply Laplace transform on both sides, V of t will be k1 e power s1t plus k2 e power s2t. This is the voltage equation. For the roots, we can find s1, s2 are the roots. Based on the roots, this expression will be expanded based on the conditions, as we have seen in the previous series circuit. We will be obtaining the roots 1 by LC. For this, we can write minus b plus or minus under root of b square minus 4 times of LC 4AC by 2. So we can assume this as 1 by 2 RC plus or minus under root of 1 by 2 RC whole square minus 1 by root LC. Here we will consider alpha is equal to 1 by 2 RC and omega n is as it is same 1 by root LC. Here zeta damping ratio is alpha by omega n, that is 1 by 2 RC by root of 1 by root LC. That means root LC by 2 RC. That means 1 by RC, as C is there. C, this can be written 2 times. First will be cancelled, root L by C is equal to zeta. This is the zeta value. And for critical resistance, to find critical resistance, the value of alpha should be equal to omega n. Alpha is 1 by 2 RC, omega n is 1 by root LC. R critical value is we can write root LC by 2C, then 1 by 2 root LC. We know here this R is given to this side, this on the top, So 2c is say as it is. This is the R critical value. We know case 1 alpha is greater than omega n, case 2 alpha is equal to omega n, case 3 alpha is less than omega n, case 4 alpha is equal to 0. These are same with the series circuit, and these are also same with this circuit. So I am not expanding this, as we know for all these cases the roots are same. As I previously discussed, you can complete this for first case, second case, third case and fourth case. Roots are same we can place here, but in place of I of t, now we are finding the v of t. Remaining all are similar. Whatever the roots come here, we will need to put in the v of t is equal to k1 e power s1 of t plus k2 e power s2 of t. In this equation s1, if you put and expand it, then we will get the transient response.